In this session, we will have a brief introduction of three basic problems of HMM. The structure of HMM can be represented by a general Markov model with a set of states S equal S1, S2, until Sn, and the output observation sequence OT. Transition probabilities A equal A11, A12, until ANN. Each Aij represents the probability of transition from state Si to Sj. The output of probabilities B is a function of the form BIOT, which is the probability of the observation OT being emitted by the state Si. The initial state distribution Pi is the probability that Si is a start state. There are three basic problems that HMM model can solve. The evaluation problem, also named the scoring problem, is to compute the probability of an observation sequence, which can be solved by forward-backward algorithm. The decoding problem, also named the matching problem, is to obtain maximum likelihood state sequence, which can be solved by Viterbi algorithm. Decoding problem corresponds to the task of speech recognition. The learning problem, also named the training problem, is to estimate HMM parameters, which can be solved by Baum-Welch re-estimate procedures. Problem 1, the evaluation problem. Given the observation sequence O equal O1, O2, until OT, and the model lambda equal pi AB. How to calculate the conditional probability PO lambda? That is the probability of the model that generates the observation. We can also view the problem as how well a given model matches a given observation sequence. The probability of an observation sequence is the sum of the probabilities of all possible state sequences in the HMM. The computation is very expensive. Given T observations and N states, there are T to the power of N possible state sequences. Even small HMM, for example, T equal 10 and N equal 10, contains 10 billion different paths. The more efficient methods are called the forward algorithm and the backward algorithm. Given an HMM at time t, the state is Si. The partial observation O1 until OT has been generated. What is the probability of partial observation sequence until time t? We define the forward variables of the forward probabilities. We can solve for alpha ti inductively with DP, dynamic programming, which is a multi-stage decision-making idea using recursive method to find the optimal path. The forward algorithm has three steps. The first step is initialization of the forward probability. The second step is induction for alpha ti, which is a partial probability at some intermediate state. The third step is termination to obtain the conditional probability PO lambda. If we examine the computation involved in the calculation of alpha ti, we see that The forward algorithm takes smaller computations rather than the naive approach to take large computations. Similarly, we have another method for the evaluation problem. It is called backward procedure, just computing in the other direction. What is the probability that given an HMM lambda and given the state Si as time t, the partial observation OT plus 1 until TOT is generated? We define the backward variables or the backward probabilities. Again, we can solve for beta Ti inductively. To make this procedure work for t equals t minus 1, we arbitrarily define beta Ti to be 1 in the initialization step 1. Then, we will have the induction backward until arriving at termination to get the probability Po lambda. The backward procedure requires calculations as many as the forward procedure. Problem 2, given the model lambda and the observation sequence O equals O1 until OT, what is the most likely state sequence S equals S until ST, so that S can explain the observation sequence O most reasonably. The solution to problem 1, evaluation, gives us the sum of all paths through an HMM efficiently. For problem 2, we want to find the path with the highest probability likelihood. A technique for finding this state sequence exists based on dynamic programming methods and is called the Viterbi algorithm. The purpose of the Viterbi algorithm is to find the most likely hidden state sequence based on the given observation state sequence. Similar to computing the forward probabilities, but instead of summing over transitions from incoming states, we compute the maximum. In Viterbi recursion, we define a variable delta Tg, which is the largest probability along a path. What we are looking for is the state sequence represented by the largest delta Tg at time t. There are also 3 steps: initialization, induction, termination, to keep track of the argument which maximize delta Tj. Finally, we read out the path to get the hidden state sequence. The reverse pointer phi Tj is used to record the previous state of the optimal path in each recorded state. Problem 3. Given the model lambda and a set of observations, how to adjust estimate the module parameters lambda pi ab to maximize the probability Po lambda? The training problem is one of the most important problems for HMM applications, since it allows us to optimally adapt model parameters to fit the training data, which can be later used for prediction and classification. We want to maximize the parameters with respect to the training data. That is to say, we are looking for a model lambda prime such as the maximum conditional probability Po lambda can be reached. Unlike the above problems, there is no analytical way to find a global maximum. but it is possible to find a local maximum by use of an iterative method. This is called the Baum-Welch method for HMM, or in a more general case, the expectation maximization EM algorithm. There are other training methods, such as gradient distance. We will focus on the most commonly used iterative procedure method. Baum-Welch algorithm is a hill climbing algorithm based on combined forward-backward procedures, using an initial parameter instantiation. The forward-backward Baum-Welch algorithm iteratively re-estimates the parameters and improves the probability that given observations are generated by the new parameters. 3 parameters need to be re-estimated: initial state distribution pi, transition probabilities aij, and output emission probabilities biot. In order to describe the procedure, first define epsilon Tij as the probability of being in state Si at time t and going to state Sj at time t plus 1, given the current model lambda and the complete observation O. It is computed based on the forward probability alpha Ti, the backward probability beta Ti, and the transition probability Aij. The intuition meaning behind the re-estimation equation for transition probabilities Aij is the expected number of transitions from state Si to state Sj divided by the expected number of transitions made from state Si. Also, define gamma Ti, the probability of being in state Si at time t, given the complete observation O, which is just the summation of epsilon Tij for all the state j. Thus, we have transition probabilities Aij equal to the summation of epsilon Tij divided by the summation of gamma Ti over time t. Initial state distribution pi is the probability that Si is a start state. Re-estimating initial state probability is easy to be expressed as the expected number of times in state Si at time t. Formally, we have pi is equal to gamma 1i. Output probabilities Bik are re-estimated as the expected number of times in states Si and observed symbol Vk divided by the expected number of times in state Si. Formally, Bik can be computed based on gamma Ti. Here, delta is the Kronecker delta function to indicate if the output is the observed symbol, which is not related to the delta in the discussion of the Viterbi algorithm. The Baum-Welch algorithm is an instance of the more general expectation maximization EM algorithm. Coming from lambda equal pi AB, we got to another lambda pi AB by the following updated rules. The E step, compute the forward and backward probabilities for a given model. The M step, re-estimate the model parameters. The 2 steps repeat until converge. That's all for this session. See you next session.